Thank you very much for Professor's introduction, and thanks for the organization, conference organization. So today I want to talk about use some solid Lewis acid catalysis for water medium Mukaiyama-aldol reaction. So firstly, we know chemical transformation is essential for all life, and also we produce many products by chemical synthesis. So for example, today so many molecules of very great complexity can be synthesized in modern organosynthesis. You see the vitamin B12 or the polytoxin, we can synthesize so complex molecule. For example, for polytoxin, it has more than 60 chiral centers. But however, we also have many challenges in in organosynthesis, such as until now for the process also has hugo waste and pollution. So from the 1990s, so green chemistry introduced by some scientists, and now so green and more sustainable process are very highly desirable. So in our group we focus on the organic solvent pollution, since if you do the organosynthesis for each student, so you will see after reaction there will be a lot of step you need to do, and you will have many chance to meet the organic organic solvents, and usually most of them have a little bit or high toxicity. So first expose when you do some experiment or some synthesis process, and after reaction you discharge in the environment, and even some a little bit will residual in the final product. But for drugs it's it's no safety. So but when we see the nature, so we usually use water as a solvent. It's cheaper, safe, and no toxic, and many advantages compared to the toxic organic solvents. But when we see the history, water is a common solvent in organic reactions. So first organo compound in human beings synthesis is urine, but definitely it produced in water. And also in the 19th century, many organic reactions are developed in water. So why water now is not very popular in organic lab? So since we develop the organometallic chemistry, and in the Nobel lecture, the Greek and the C, so water decompose the organic matter so very quickly. After that, so in organic synthesis, many lab we use a dry, and they don't like the water. But the interest in water as a solvent is like in 1990 with the introduced the green chemistry. And after that, also people want to use the solid heterogeneous catalysis process, since it easily recycle and reuse, and for many times. So in our group, so recently, so we want to do some solid Lewis acid in water medium reaction, since we know the traditional Lewis acid such as titanium, like that, it will decompose quickly in water. So that's why we want to develop some new solid Lewis acid, and so for the heterogeneous catalysis we hope we have a high surface area support, So here we choose the mesoporous, silica firstly. So you see how we do this solid Lewis acid. We choose the benzene bridged, organic, inorganic mesoporous silica. And we transfer the benzene to the some, ligand, functional ligand, and react with the scandium, triphi, and generate the phenyl, solid Lewis acid. And firstly, we want to determine the chemical composition. So first, we use the solid NMR. So compare the benzene bridged PMO. You can see for the carbon, there are some new peak. This is means the triflate carbon in this group. Also XPSC. So you can find the scandium metal. This active sites could be found in our catalysis. And also you can compare the homogeneous catalysis scan triflate. So the peak have a little bit shift. That means the active sites have some coordination with our support. And also we use XID and TM, also some nitrogen sorption, and this mesoporous Lewis acid has ordered, pore structure. After that, we want to choose, Mukaiyama-aldol reaction. It's like it's a one important carbon-carbon formation, reaction, and particularly we choose a formic acid as a reactant. Since formic acid, we use formic acid, aqueous, aqueous, solvent. We don't use the gas. And since this is much cheaper, and also, it's very easy to prepare. And as first way, to do some reaction condition and catalyst scan, and we found, so we determined the good, reaction condition, and also we tried the different, catalysis, and we found that this reaction, scandium triphi, functionized the solid Lewis acid is a good one, and they can get the yield about the 90. And interestingly, we compare we first compare with the homogeneous catalysis, scandium triphi, and you can find, so for the homogeneous, the conversion is very low. And also we prepare the control sample is SBL 15. This is a no, benzene bridged, organo, some no benzene, just silica, no hydrophobic benzene inside the pore wall. And we found also it has a little high conversion, but compare the selectivity. Why does it have a selectivity? You can see, so for the sanin also will be hydrolysis to the ketone. And it for the SPS 15, it doesn't have hydrophilic benzene inside the pore wall, so its selectivity is very high. So compare these two control samples, we think our benzene bridged mesoporous silica is a good support for Lewis acid scandium triphi. So why? So we see the reaction mechanism. So we first, so this Lewis acid react with the formaldehyde and generate intermediate, and also the sanin will react with this intermediate, and finally generate the final aldol addition product. Also the water will interact with the sanin, generate a product, byproduct ketone. So for our system, so in the pore, the Lewis acid, exactly inside the pore. So since the silica is hydrophobic, but the formic acid is hydrophilic. So in our system, so the solid catalysis has a high, surface area, and also it has, hydrophobic, surface. It will, concentrate the hydrophilic, the formic acid, and hydrophobic, saline together, and get a very high, conversion and selectivity. For the homogeneous catalysis, it could not, get these two different properties, reactant, interact, efficiently. And for the SPF 15, I mean, this mesoporous, just a silica, since the surface, philic, the surface, some, OH group will, generate a lot of byproduct. So that's a reason for our catalysis advantage. Also, we do some structure activity relationship. So we use our catalysis to adsorb some a vapor adsorption test. You can see for our catalysis, so it adsorb a lot of toluene, but toluene. But it's very adsorb a very a small water. So it means it could selectivity to adsorb some reactant, and also we do some benzene aldehyde adsorption test. You can see compare SPF 15, it could be selectively adsorb benzene aldehyde. And also for the solid catalysis, we need to do a recycle. You can see for our catalysis, we can recycle for more than 10 times. But for the control sample, SPF 15, it only just 3 times. So we test why, since for SPF for our PMO, this catalysis, so the active side just contact with the benzene sodium light ligand inside the pore wall, but SPF 15 is not that way. So it means for the scandium leaching is very high for SPF 15. And also after reaction, we calculate the recycle catalysis. It also have a ordered mesoporous structure. So after that, since the benzene bridged PMO is very expensive, so we want to use a cheaper one. So we choose a phenyl formaldehyde polymer resin to support Lewis acid. So we just intended the benzene bridged silica to the resin polymer, to the benzene formaldehyde polymer. It's very cheaper, and we do it with a mesoporous structure. And also, firstly, since this one doesn't report by any groups, so when we do the catalyst, we very carefully to do something control. So with first optimization of the sulfur in our support, and after we try the different things, we found use this acid and a solvent is a DME. And after that, we need to optimize the measure, ETM YB, this active side, and get the good, it's a very high, active side contains. And also we do some, chemical composition, analysis, use some XPS, and we, demonstrate this Lewis acid inside our, support. And also even for the polymer, we also can be get the ordered, mesoporous structure. And we do some reaction, condition optimization, and determine the reaction. We do the same reaction like the silica, and its reaction temperature is 20, and the catalytic loading is 7.5, and we use 10 equal, formal acid. And we also scan the different catalysis, and we found in this system, so YB triplet is the most, is the best one, and also better than the silica, supported Lewis acid. And also we compare the homogeneous catalysis and the commercial polystyrene supported Lewis acid. We also found that it have a very high conversion and a similar homogeneous catalysis selectivity and a better selectivity than commercial polystyrene supported Lewis acid. And we also use the vapor adsorption example, test to demonstrate our, mesoporous Lewis acid has a more hydrophobic, surface properties, and also it can be, adsorb a lot of, hydrophobic, reactant in our system. And we also do some substance. We directly can be determined. So if the formic acid can be efficiently, adsorbed by our, catalysis, it's much better than the traditional polystyrene supported Lewis acid. And this is formic acid, adsorption test, and this is for the silicon adsorption test. So this test, definitely, confirm our advantage. So in the, mesoporous resin support, Lewis acid catalysis. Also, we try the different, substance. All this get the, good result. And also we can find this, mesoporous polymer support Lewis acid have extended with, stability in our water medium, Mukaiyama-aldol reactions. And this is summary. So we develop, mesoporous Lewis acid by, just transfer benzene to the Lewis acid. And also they have a significant high, catalytic efficiency and homogeneous catalysis. Also some commercial and traditional catalysis. And also it will be very stable since the Lewis acid is inside the mesoporous framework. It can inhibit the active side leaching and have a high solubility. So I need to thank funding from China NSF and some Shanghai government. And this is two guys help us to finish this work. So this guy is come to Northeastern Universities, United States as a PhD. And this one is to a famous company in China. And finally, thank you for attention.
Thank you, Doctor. Do we have any questions at this time? Anyone like to ask any questions? Where? Oh, go ahead. You just use that mic right there. You're fine.
So, in terms of the substrate pre-concentration, does that also mean that the product would also be retained within the active site region? And would product release ever become rate limiting?
Yeah, it's a good question. Since after reaction, so the product can be released since the reactant want to interact with the active site. I think.